but I will start the presentation now. So I'll talk for 45 minutes. Please ask questions as and when you think of them. You can just pop them in the chat and I will try to get to them immediately. I'm here on my own. I normally have a person next to me who checks on all the questions. So let's make a start. I am taking it. Now, my company is called QECWA, the Quantum Education Center of WA. If you can just write down QECWA, which is QUECWA, because there's lots of information all freely available on my YouTube channel. So I do encourage you to subscribe. So let me start. I hope you can all read the Chinese wording on the screen. This is the magic of quantum computing. And trust me, there's two things you need to take away from this. One is that quantum computing is going to change everything. It's not just a normal technology that's making things faster. It's totally different. It works on quantum physics, which we still don't understand. It's quite feasible that within a decade, our society will be run by computers that we don't integrally understand how they work. And that sounds weird, but it's going to get weirder. But the important thing is it's exciting. China's leading. And basically, there's a huge, challenging professional career ahead of anybody who wants a career path. Teleportation. Now, I normally ask a question and I say, imagine I put a little speck of dust on my hand and I go, boom, and instantly that speck of dust is now 150,000 kilometers away on a orbiting spaceship. So I asked my young audiences and they look at me as if I'm a little bit mad. So I'm telling you, we will have the technology to teleport a little bit of dust, a little piece of matter from my hand, from a laboratory on Earth to an orbiting spacecraft. And then I say, when do you think this will happen? Do you think it'll be in 10 years, 20 years, 100 years, or do you think it will never happen? And of course, people give different answers. The answer is it happened 5 years ago. We have already done that. The Chinese have done that. And I'll be introducing you to the professor who did it on one of the slides. So it's amazing stuff. It is magic. Now, I'm telling you that it means everything, but let's just see what, one of the world's richest, wealthiest men who actually did study quantum physics, Jeff Bezos, founder of Amazon. Now, I must admit, I normally don't listen to wealthy people. They don't have anything to tell me. But in his case, he is saying, and he said this just a couple of months ago, quantum computing is the future. I am not exaggerating when I say it will change everything. And he's right. It's just going to improve our knowledge. It's going to allow us to do calculations that we have never, ever thought of possible or ever been close to doing. And hopefully today I'll get over why that is so. There's still people coming in, which is great. Don't forget to hit the chat if you have a question, and I'll get to it as soon as I can. Australia and the CSIRO, who I work with, are putting lots of money into quantum computing. Every single government in the world, every single large corporate in the world is looking at quantum computing because, like Jeff Bezos says, it's going to change everything. Australia has promised a large investment, and CSIRO, they're our Commonwealth Scientific and Research Organization, they've actually said that, look, quantum computing within the next decade or two, will be employing 16,000 jobs in Australia alone and creating over $4 billion of business. So this is serious stuff, and it's a fantastic career. Now, let me start. I'm going to give you a few facts, a few fun facts. They're all real, they're all true, but they're funny and it'll make you think. And then I'll talk about quantum physics, what it means. And quantum physics is crazy, but we'll talk about that in a minute. And then the magic of quantum computing. So let's start with some facts. Excuse me while I read it. Hopefully you can read that behind me. But the fastest classical digital supercomputer in the world, the fastest computer in the world, can perform 200 quadrillion operations per second. Now that's impressive. And this is what we call a classical computer. It's digital. Quantum is completely different. But you have to say, isn't it amazing what classical computers can do? Well, it is, but it's more amazing what quantum computers can do. Pan Wei from the, I hope I pronounced that correctly, from the Chinese Scientific Institute, he's actually, they've announced that they can have a quantum, they've got a quantum computers based on photonics, which is light, which can operate 100 trillion times quicker than that amazing classical computer I just showed you to. And when we talk in trillions, it's unbelievable. This computer, the quantum computer by Pan Wei, actually performed the calculation which would take the fastest supercomputer on Earth half the time of the evolution of the solar system to have done. It did it in a few minutes. This is what we're talking about here. Quantum supremacy, classical digital computers use bits. So no matter how big the current computers we have, the ones that operate on the cloud, when we do a search in Google, it has 100 million records it finds instantly, uses bits. Quantum computers use quantum bits, which are qubits. And when we have 300 qubits, now listen to this, we'll be able to map to reference to the, to the equivalent of every single atom in the observable universe. These are the sort of figures we're talking about. Now, what you have to remember, quantum computers work at the speed of nature. They are exponential, whereas every other computer is linear. And to tell you the difference, how many different place settings do you think you can have if you've got 10 people at the table? This is a good question to ask at dinner. Imagine just an ordinary table with 10 people. You could have Wendy on my left, or I could put Wendy on the right, or I could put Wendy at the other end, and keep putting all the different people in different places. How many different settings do you think we could have? The answer is 3.6 million. Yeah, did someone say I was going to say that? That's wonderful. Well done. It is. It's 3.6 million, the factorial of 10. And the important thing is it increases exponentially. And this is what nature does. And this is what quantum computers do. This is why soon, well, not soon, we're already solving intractable problems, problems that supercomputers could never solve. We're already doing it, and we're understanding things like bird migration, photosynthesis, simulating the Big Bang, creating vaccines that will work, having weather predictions that are totally accurate. There are two things just to bear in mind, I'm skipping ahead, but two things that quantum computers do exceptionally well, and that is simulating and optimizing. And you may think that's no big deal. Trust me, everything works. Every computer program works on optimizing. This is fantastic. Okay, let me give you an idea. Next time you go and you get some money out from an ATM and you use your PIN is encrypted. It goes through a hashtag and then it's encrypted, sent to the bank, decrypted, and you get your money. If we could take that transaction, we could record the transaction, and if we had the fastest computer in the world try and get your PIN, it would literally take it 3,500 million years to get your PIN. So you're safe, or are you? Because with a quantum computer, it could get your PIN using a thing called Shor's algorithm on a fault-tolerant quantum computer, so it's a way off, but don't worry, it could get your PIN in 6 seconds. Okay, excellent. So look, you know, this is unbelievable. And for the first time ever, we're going to have 100% security. When I did my master's in 2001, one of the questions was always, can you have an unhackable code? And back then you couldn't, because any operation or state transformation you put onto the code could be reversed. But in quantum computing, it is truly probabilistic. We'll get into that. I'm going to go way over time if I carry on. But I did want to tell you, here's an experiment. It's called the most unbelievable experiment ever conducted. It was only conducted, again, by Chinese scientists in the year 2000, 20 years ago. It is the delayed quantum erase experiment, and it shows some weird things happening. It seems to be that events that have already occurred can be changed. So things have already happened can be altered. It affects time, it affects distance, and it all gets back to quantum entanglement. And I'll explain quantum entanglement very shortly. In fact, I'll be doing it now. Quantum computers are merely quantum physics, the laws of quantum physics, which are very weird, very strange, doing computations. And they do computations exponentially, and they can transfer the data instantaneously over hundreds and hundreds of millions of miles, just like that teleportation I was talking about before. So what is superposition? Now, when scientists first discovered quantum particles, now quantum is anything smaller than an atom. So when you've got an atom, inside that atom, you actually have particles. You've got proton, neutron, you have electrons, you have gluons, you have quarks, you have many, many subatomic or quantum particles. Now, when scientists first discovered these quantum particles, they couldn't believe what they saw. These quantum particles behave, and by the way, these quantum particles are in you, are in the table, are in the chair, are everywhere. You are a quantum particle, a quantum object containing quantum particles. Yet these quantum particles do strange things. They are in multiple states at the same time. It's like being on and off at the same time, hot and cold at the same time. And not only are they in all of these states at once, it could be millions of states. So whereas when a bit, and I know some of you will know this, the bit, a binary digit, can only be 1 or 0. Every single computer, not counting quantum is completely different. Every other supercomputer or normal computer, everything you've got on your laptop, etc., works on the fact that it represents 0 and 1, on or off. It uses transistors. Is there voltage? Yes or no? Is it this kind of voltage? Yes or no? But in the quantum world, we can be yes and no at the same time, and a multitude, an infinite number of variations between on and off together, represented by a thing called the Bloch sphere. So write that down, B-L-O-C-H. We'll touch on it later because that's one of the most important things. Now, just to talk about superposition, in 1801, so over 200 years ago, Thomas Young wanted to know whether light was a particle or a wave. And he set up an experiment, this is called the beautiful experiment in science circles, because it's so easy to explain what it is. And it is so amazing. I don't have time to go into the ins and outs of the double slit, but it was amazing because it showed that light was a wave and a particle. Because 100 years later, Einstein proved that, which is with a thing called the Einstein and the photoelectric effect, Einstein proved that light was a particle, even though Thomas Young in the previous slide proved it was a wave. And we found out that it was a wave and a particle at the same time. And this effect, write this down because this is the be-all and end-all of everything, it's called superposition. And when you measure that superposition, it becomes a definite position. I know it's difficult to understand. Don't try and understand it all, but just see the importance of it. Okay. And we can prove quantum entanglement. I could go into your body, take out an atom, take out those 2 protons or neutrons inside or electrons, and I could entangle them. And then I could put one on the moon and one here. And when I change the one here, the one on the moon immediately changes. And nobody knows why. Nobody knows how. Einstein even said, oh, this isn't happening. He called it spooky action at a distance. He said, look, it's happening. I can see it's happening. But we can describe it in classical terms. Einstein didn't like it because something was happening faster than the speed of light. Because when I say instantaneous, I mean it. Something is somehow communicating with another subatomic particle 1 billion miles away. It doesn't matter how far the distance is. And it doesn't matter the time as well. Quantum entanglement goes over time and goes over distance. And believe it or not, we can build computers out of this stuff. We now know that it's true. There have been many, many, many experiments. There's a thing called Bell's inequality and what's called the CHSH game. If you like games on computers, get onto the CHSH game. It proves that something strange is happening with quantum entanglement, something spooky, and it's involved with black holes as well. And you can go from one end to the other of the universe, traversing immeasurable distances. This is so exciting. Now, in classical physics, if I put a point, if I've got a fly is here, and I want to say, where is that fly exactly? I can give you coordinates along 3 measurement bases, we call them components, X, Y, and Z, and then you can, in a 3D, work out where the fly was at that moment in time. Now, in the quantum world, you're not allowed to know. It's called Heisenberg's uncertainty principle. And unbelievably, believe it or not, you cannot know the momentum and the location of a subatomic particle because it has a probability of being everywhere. This sounds really strange, but it's really true. It's been proved many, many times. And we've now got computers running on this. Oh, now this is the wonderful, wonderful Bloch sphere. So as I said to you before, classical computers rely on bits that can only be on and off. So boring. And you can't entangle them. In the quantum world, these quantum bits, qubits, subatomic particles, quantum particles, can be a probability of being everywhere at once, and they can be connected over billions and billions of kilometers. And we can use linear algebra. By the way, if any of you studied linear algebra or studied Python, you're way ahead, well done. But we can actually make computations. We can conduct state transformations on these three-dimensional quantum particles that we don't know how they work. We don't know how they talk to each other, and we don't know how they're in every position at once, but they are. Now, but quantum physics is weird, so quantum computing is weird. Quantum computers cannot tell you what the answer is. It's like me having the best calculator in the world, and I say to Wendy, Wendy, I've got this calculator that will do every calculation you've ever thought of, all these complex engineering calculations, it can do it instantly. But when I show you the answer, it will only be a 1 or a 0. And please write this down. It's called collapsing the wave function. Remember before I said to you, a subatomic particle is always in a state of being everywhere. But when you look at it, when you observe it, when you measure it, it goes to one point. And it's the same with a qubit. And it can do this great big calculation, but if you say, okay, tell me what it is, I want to measure that calculation, it will say, it can be a 1 or a 0 with equal probability. Now that's really important. Einstein said, it can't possibly collapse to 1 or 0. And we, he said, we must live in a deterministic universe. We should be able to work out, do the same function twice, and it'll always be the same result. But no, in the quantum world, it is truly probabilistic. And this is where we get to, Einstein said, God doesn't throw dice. This is where we get to a thing called the many worlds theory. The many worlds theory is that there are, the collapse of the wave function happens in one universe, and then when there's another collapse, another universe is created, another world. It sounds absolutely weird, but there's a lot of scientists who believe that. We haven't proven that yet. Very difficult to prove, as you can imagine. So can you believe that? I know you guys are probably thinking, Eamon's talking a load of rubbish, but I assure you I'm not. And I assure you the Chinese scientists like Pan Zhanwei, he's the leader in the world. And they're doing very, very strange stuff. They've got clones now that are quantumly entangled. So there's instant communication. Amazing. Classical computers can only be 0 or 1. They can't entangle with another. What they just do is by cleverly using a binary system of 0 and 1s, they make fantastic calculations, the likes of which run the internet and have run everything we've ever had. Whereas quantum computers use qubits, which they have an infinite number of reference points like on the block sphere, that we can refer to and we manipulate it. We actually can send microwave bursts of different varying intensity and duration, and that will change the subatomic particle into different superpositions. Amazing stuff, and China's doing great stuff with this. I don't think we can go too much into the quantum gates. I just want you to know that it's all relatively simple. Just as we have classical gates, logic gates to do state transformations, you know, in normal computers, we have the same quantum gates to measure state transformations. And it all looks a little weird, but I'm going to show you in a couple of slides how you can log on to a real quantum computing tomorrow and do real quantum programming virtually straight away. It doesn't take long to learn this stuff. And by the way, I'm liaising with Wendy, and I'm going to hold some classes for members of the ACFSWA. So we're going to work that out. Very exciting opportunity. Now, all I wanted, this looks confusing now, and I don't want to confuse you, but the gates are merely represented by matrices. And the matrices are not that difficult to follow if you've done any linear algebra. But the important point is you can get up and running with this really quickly, and you can actually then test it out on real quantum computers. Unbelievable. And here's the link. Please take down this link, or I'll give it to you again. But if you register with IBM, and there's many of them now, it's not just IBM, Microsoft do one, Amazon do one, you log on, you register, and then you have access to their cloud quantum computer, the quantum cloud. The quantum cloud has 100% security. Now that's a good and a bad thing. If you think about what the dark web is like now, it's like giving all these criminals a real way to transfer information that can never, ever, ever be decrypted because it's based on probability. This timing's going really well. I've got 10 minutes and then we'll have 15 minutes questions. So you've got a real quantum computer at your fingertips. You just register this easy. And this is what a quantum program looks like. It's very graphical orientated. I don't know whether you can see my mouse. I don't think you can. Oh, doesn't matter. I wanted to get hold just to show you, but you can see these gates here. You really, with these squares with gates inside, all you do is drag them onto the qubit. And then it does all the calculations for you. It is fantastic. And the takeaway I want you to take away from this is that it's not difficult to do, and it's exciting and interesting. You young people and old people as well, but young people, you are gonna, right now, there's people, corporates throughout the world looking for quantum application developers. I might add, there's no program that's running on a quantum computer yet. We can run meaningless tasks like we did, which was the Gaussian boson sampling for the quantum supremacy. But this is an open opportunity. And the good thing is, all the old people like me with the IT skills, we have to start again, whereas you come into it fresh. Yeah, quantum supremacy, Google, NASA had a collaboration, and they performed quantum supremacy on a 53 qubit chip. And when I say 53 qubits, they all worked only for a couple of microseconds before they collapsed. So we're not at the stage yet that we have what's called fault-tolerant computers, but it's coming. But So China has improved on these results. I can't quite remember. I think it was, oh, I've got the date there. Yeah, 2019, just 2.5 years ago, Google did what we call quantum supremacy. There's a bit of conjecture about whether it happened or it didn't. It doesn't matter. It shows that the quantum computers, even though they're very, 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 very primitive, they only last for microseconds. They can do intractable calculations that the fastest supercomputer on Earth simply can't do. And the China scientists are now doing calculations hundreds of thousands of times quicker than Google did in 2019. And I reckon within 18 months, and I'm already working with some application developers, we will have proper quantum applications for simulation and optimization. And there's many, many algorithms that work on that thing called the Monte Carlo simulation. So it's amazing. And there's China. You may think I just put that slide up for you guys. I didn't. That's part of my presentation when I'm telling people globally how China is so far ahead and doing some amazing things. So the advantages, the takeaways to remember is that when it comes to simulating nature, simulating weather patterns, that's nature, simulating so much that from the Big Bang onwards, quantum computers can do it in a way that classical computers never ever could. And that's like, remember I was talking about the 10, how many ways can you set up 10 people around a table? That's the reason why we can't do viruses is that the virus is a transformation of atoms and molecules. And as soon as you've got an atom with 10 electrons and they want to exchange them with the virus to take away from the virus, we can't simulate it. It's like, that's why our vaccines are so average now. It's like saying, what did you think of that movie? And you only watched the first 15 seconds. But soon we'll be able to fully simulate COVID-19, et cetera, et cetera. Optimization is so important for banking, huge. The finance sector, there's a thing called portfolio optimization. So when you've got these finance companies that have thousands of shares, they need to optimize the buying and selling and the derivatives. And it's all based on what's called the Monte Carlo simulation. And they do that now classically, but the quantum will do it literally hundreds of thousands of times quicker. Also things like freight optimization. There's this thing, a mathematical riddle called the knapsack problem. Don't know whether I mentioned that. The KNAP-SACK, where you have variables with different values and you need to optimize them. It sounds like it's not a big deal. It is a huge deal in almost every industry, like the material industry, the manufacturing, etc. And then there's the UNC. The UNC is the unknown unknown. I noticed Mel couldn't translate UNC, and I'm not surprised because it's not a real word. The UNC is a science jokey word that means the unknown unknown. And what we're saying is we know, without a shadow of a doubt, that quantum computing is going to solve issues we haven't even thought of yet. So we've got the finance sector, international freight, etc., etc. So that's, oh, I don't want to end the meeting. Let me now stop sharing. Wow. Nice. Hello, Wendy. Nice to see you.